Hi guys, here's another video on topic 5 on electricity. This one's dealing with the topics of resistance and resistivity. So the learned objectives are that you will understand what is meant by electrical resistance, you know the factors affect resistance, and you understand what is meant by the term resistivity and how you can calculate it. Here's your key ideas you should already know, many from GCSE and previous lessons. Resistance is a measure of the opposition to current. We measure resistance in ohms, which is given the omega symbol. The larger the resistance, the smaller the current, and if the resistance decreases, then the current will increase. Some more key ideas. Resistance is often high, so may be quoted in kilo ohms or mega ohms. A kilo ohm is 1,000 ohms and a mega ohm is 1,000,000 ohms. You could go up to a giga ohm, but that would be a very large resistance. If the resistance is very large, then the current is going to be very small. So maybe quoted in milliamps or possibly even microamps. Make sure you know your prefixes. A milliamp is 1,000th of an amp, or 0.001 or 10 to the minus 3. And a microamp is 10 to the minus 6. And it could be a nanoamp, which would be 10 to the minus 9 amps. Okay, the equation. This is one of the most common equations used on A-level papers. Potential difference is current times resistance, which you should have learned at GCSE, but it's on the equation sheet. Make sure you know your symbols. V for potential difference, sometimes known as voltage, but we'll stick with potential difference, measured in volts. I is in current, is measured in amps, and R is resistance, measured in ohms. You must be able to rearrange it, so I would be V over R, and R would be V over I, which is how you would calculate R, and in fact is a definition of resistance. So, the effect of temperature on resistance. Resistance is a characteristic of all materials. Some, like air, has a very high resistance, and some have a very low resistance, like gold, which is one of the best conductors. Electrical resistance is similar to friction if you think about it in terms of forces. It is a resistance to movement. Electrons drift slowly, very slowly through a conductor when a voltage is put across the ends. The metal atoms interfere with the motion of electrons, causing resistance. So you can see very much like friction, where the electrons have to fight their way through the metal atoms or ions. The higher the temperature, the faster the metal atoms vibrate. So this doesn't show it on here, but those atoms are vibrating. And if they vibrate more movement, and then it's going to impede electron flow, hence increasing the resistance. Okay, now we come on to Ohm's Law, developed by George Ohm. Ohm stated that a current in an ohmic conductor, one that obeys its law, is directly proportional to potential difference across it, provided that the temperature and other physical conditions are kept constant. So at A-level, often these laws, obviously a law can't be broken, have caveats or conditions attached to it. We can write voltage as proportional to current or directly proportional to current. In symbols, would use a proportional symbol, and to put the constant in, R is a constant, and that would make it complete. Remember, R is measured in ohms. So I'm going to show you how you can find resistance from a graph. Compare the equation for an ohmic conductor to the general equation for a straight line. So V is proportional to I, where R is a constant. You can compare that to the straight line. So if the graph is plotted with voltage on the y-axis and current on the x-axis, and you can do it either way depending on which variable is your dependent and independent, it can be seen that the gradient will in fact be the resistance. So there you go. You can hopefully see that the gradient is V over I, and V over I would become resistance, and it will go through zero because it's a directly proportional relationship. I've put both sides of the origin there, so minus and positive, because it doesn't matter which direction the current is going. If you plot it the other way around, the voltage current graphs are often drawn the other way around, then the gradient would be I over V, which would be 1 over the gradient. Okay, just to recap on equivalent resistances. So you might have something drawn quite complicated here. I'm going to show you the method. We try and get it down to one effective resistance. So for this equation, for this circuit, I'm going to show you how to do it down to 1. What is that equal to? How you do it is you get all the ones in series. It's quite simple. You just add them together. So if you had a 10, 20 and 15, add them together to get 45. The general number of resistors, you can just use this formula, just adding them together. Very, very, very simple. For resistors in parallel, to work out the equivalent resistance for a resistor, a more complex equation is used. So it's a reciprocal 1 over. So for example, if you had these resistors in parallel, then you'd add 1 over each of them, 1 over 10 plus 1 over 20, 1 over 15. And you could do it in fractions, get a common denominator, and here is 60, and get an answer of 13 over 60. And then don't forget at the end, to get the resistance, you would take the 1 over that, so it'd be 60 divided by 13. Or you could put in your calculator as decimals, again not forgetting to do 1 over the reciprocal at the end. Now we're going to introduce the topic of resistivity. Let's start by having a look at some examples. Here's 4 materials: copper, silicon, silver and plastic. So if I was going to ask you which one has the highest and largest resistance, you may say copper or silver being the lowest, which would be right. You may say that silicon or plastic being the highest resistance. But between the copper and silver, which one has the highest and the largest and smallest resistance? Well, it actually depends on the size as well. So the silver one there, being a bit shorter and a bit wider, is likely to have a lower resistance. We're going to explain this with the term resistivity. So the measure of how much a particular material opposes electron flow is called a resistivity. That's unique to a material. I'm going to try and explain this to you. So resistivity is usually given the symbol rho. It's a Greek letter. It's the same symbol as is given to density. Resistivity is calculated using the following equation. It's the resistance times the cross-sectional area divided by the length. In symbols, RA over L. That's an L, not an I. And you'll find this on your data sheet. Okay. The units of resistivity is the ohm meter. If you didn't know that, you could work it out, because R is in ohms, A is in meters squared, and L is in meters. So the meters squared M cancels out, and you're left with ohm meters. Resistivity for a particular material varies with temperature, so it is usually quoted for a particular temperature, usually at room temperature. Here is a table of typical resistivities. They're all metals. Usually would just be measuring metals. If it was non-metals, then the resistivity would be much, much higher. You can see these numbers are very small. They're all 10 to the minus 8 or 10 to the minus 7, meaning that they're very good conductors or that they have a very low resistance. So copper, it's accepted that its resistivity is 1.68 times 10 to the minus 8. You can work out the resistance of a particular type of copper, or shape of copper I should say, by putting in the equation the area and the length, and you can work out the resistivity, which is what your task is going to be. So thanks for listening, and you can move on to the task.